is a problem for them. So what drives the storage problem? Now fundamentally, the problem is lack of trust. And this is sort of the key feature of blockchains, that you don't have to trust anyone. That's the way I would like to put it. But in terms of the algorithms, the underlying layers, they cannot assume that other parties in the network are good faith players. So that means you have to validate everything. So you have to validate the entire chain, that essentially means that the fundamental way to get up to speed with the chain is to verify every block, every transaction, every state on the chain. Now, another thing I would like to, I think, introduce here is what I would call the one-chain mentality. For full-timers like me, I guess it would be the Highlander mentality. If you've seen the movie Highlander, there can be only one. That's kind of what it's. And there are two things I think driving that. One thing is you want people to trade on your chain so that can drive up the price and make you richer. But also the thing about how blockchains work. The bigger you are, the more robust you are against brute force attacks. So that is also a reason to want to congregate on one chain. Another thing that drives the storage problem is functionality. We want to do more faster, right? So more, when you stack up more features and more kinds of state on the chain, that means more data that's being maintained. And also, if you crank up throughput, that means your chain is going to grow that much faster, right? So, arguably, in the race for faster and faster chains, you could say that just fast enough, at least in terms of the storage problem, is probably the best place to be. If your actual throughput is in the order of one transaction per second or something, why do you want to have a maximum 2,000 transaction throughput or something? Means you're going to collect data much faster. So how do you mitigate this? Well, you can kind of cheat. You can develop a light client that just essentially trusts that there are nodes out there, they seem to know what they're doing, they seem to be following the main chain. I'll just jump up to where they are, and then I'll follow the problem. Essentially, you're trusting that the network is in a stable state. And this is fine in many cases. Other ways to cheat is you try to do as much as possible off-chain. I call that layer 2 magic. I remember hearing a Bitcoin fanatic saying that, hey, you can do anything basically with purple trees offline, and then you just post the root hash on the chain and we're fine. So that's basically putting as much as you can off-chain and then storing as little as you can on-chain. You can also prune the chain. I will talk a little bit about garbage collection, how that works. You can also do lighter versions of sync. One thing that we're working on is what we call spine sync. You just sync the key block headers, and at least you verify that the key blocks are connected to the chain, and you check the previous hash and everything. So you feel that you have a robust spine, but you don't care about the state until you start approaching the top. You can also do snapshot sync. This is something that Ethereum has, and we're kind of copying now. Some other chains have zero-knowledge proofs where they essentially run through a very well-defined algorithm and accumulating a proof so that you can say at this height, like 500,000 blocks from Genesis, if you just evaluate this proof, you will know that this block is connected all the way down to the Genesis block and it follows all the rules. Now, in order to do this, you have to have an abstract model for all the functionality on chain, essentially. And the more functionality you have on chain, for example, as æternity does, the harder it gets. But there is another way to do this, and that's to partition the problem. So you can do parent-child chain setup. Now, this is done in different ways. Like there are, for example, some chains that connect using merge mining, stuff like that, that basically build on the security of the Bitcoin chain. And some burn Bitcoin to establish, to mint coin on their child chain. So essentially they piggyback as closely as possible the security of Bitcoin and also sometimes on the value of Bitcoin. And then they have their own chain that they can manage for specialized purposes. And so one of the things about partitioning blockchains, partitioning is a very common method for distributed databases, where you have lots of segments that are spread out that look logically as one segment. Now, if you do that in blockchain, and it has been done, essentially, when you get down to the core logic, all those fragments are essentially their own chains. And you have to do atomic swaps between segments. So you can even have a network of separate chains, or you can basically present it as one chain, and internally they're essentially separate chains. And this again goes back to the no trust model, because if you're in one segment and other nodes are managing other segments of the chain, you can't trust them, so you have to validate everything. So essentially you have to treat them like a separate object. So then the way you actually communicate between them is with the atomic swaps. So state channels is another thing that can mitigate the storage problem, where you basically take some resources from the chain, you put them in an off-chain channel, and then you can interact with tons of transactions, and then you can checkpoint the states later. So that, and also, if you do that, you actually achieve privacy on those transactions. So you can do a lot of stuff off-chain, but still in a secure way, where everything is co-signed, and then you checkpoint the balances to the chain. And of course, that also means that you don't actually store all the intermediate states, which does mitigate the storage problem. So how is state stored on the blockchain? Now we're going to get down and dirty. The thing that's used, and this is from the Ethereum documentation, is called the Merkle Patricia tree. A Patricia tree, I don't know if all of you have computer science background, but tree structures is usually where you are very commonly used in programming to achieve fast access to data. And a Patricia tree is a little bit special because the key, which is normally sort of stored together with the value down in the leaves of the tree, becomes the path to the network. So we split the key into 4-bit segments, and each level then, or the 4-bit segment becomes a branching value. So here you have a branch node with 16 slots, 0 to 50. So you take the next 4 bits of the key, peel them off, and then you look at the value. 4 bits is 0 to 50 in binary representation. So then you find a slot here, which points to another node in the database. And eventually, you can get down to a leaf node where you find the value and the final bit of the key, or final part of the key. So what happens once you inserted that is you hash that node, and then you take that hash up here, you hash all these subnodes, and then you get a hash here, and then you get a hash here, and then you have a top hash. This is called the root hash, and that you store with the block. So for a certain block at a certain height, you get a root hash, which points to a unique slice of this tree. So at every height, you can get a separate slice of the tree, which is the full state at that height. So the nice thing about this is that when you then add another block, and then you maybe change just this value, then that becomes a hash which updates this hash, which updates that, but all the other pointers are the same. So you only change the elements that are in the path of that value that you're updating. So it becomes very economical, so you can basically store millions of slices to this tree, in this tree. And you can just go back in time, and you can find a slice and just see exactly what the values were at that time. So that's very nice. But if you think of your account, for example, and while it will be interesting to some people to see every single balance at every block height since the dawn of time, in many cases we may not care. So maybe we only care about the state, to have the full state in the topmost 1,000 generations of the chain or something. Before that, we don't really care, because we're never accessing that data. There may be nodes in the network that are archive nodes that have the full chain, but in many cases, with our own node that we're running, we don't care. So then we can run garbage collection. Basically, all the slices that are in the past, far enough in the past, we can just delete them. But how is this done? Well, the way we do this is that for each state tree, we have essentially two database tables. One is active, one is passive. And anytime we want to look up a value, or this is actually inserting, if we insert a value, we always do this in the active copy. If we want to look up a value, we first try the active copy. If it's not there, we check the old copy, which is the B copy. If it's not there, it's not in the tree. If we find it there, we move that to the active copy and then we return it. So that's this, what this illustrates. Now, so this means if we swap, we can clear the B table and then we can make that the new active, and then we're writing new copies in the new active, and then we promote values from the old copy to the new on demand as we read them. This is fine, but that only takes care of the state that we actually touch in the following blocks. And the idea is after a certain number of blocks, say 1,000 blocks or something, we just clear the backup copy and we make that the new one. And then everything that was in there that hadn't been promoted is gone. And then we start. The thing is, when we do that swap, we actually have to run a full pass at the entire state. We have to touch all the state elements that are actually reachable at that height. There's really no way around that. Anytime we do a swap, we have to scan the entire state tree. Now, luckily, we can do that in the background. Say that we were going to do the next swap in generations or 1,000 generations, we have lots of time to do the scanning, so we can slowly walk through the entire tree and load all the values onto the table, and then when we're done and we've reached the height for the next swap, we just clear this table and then make that new table and then start. So, easy peasy. Actually took a little while to get this right. Now, there are complications. Like, there could actually be sibling blocks at that height, and blockchains are eventually consistent, so they may actually become a main fork later on if they are new blocks are added onto those siblings. And if we didn't scan the state of those siblings, we will lose data once they are promoted to become the main fork. So what we have to do is, when we've done a swap height, if a sibling appears at that height, we have to scan that too. We have to scan that slice of the state to make sure that we're also up to date on that. So this actually works on mainnet. Since very recently, we had an older version of garbage collection that only collected accounts. Also, it wasn't really extensible for various reasons. This one actually garbage collects all trees, and you can download backups. We prepare backups that are snapshots of the database. The full backup right now is 134 gigabytes. What it was, that's actually on 23rd of August, so that's the garbage collected. Garbage collects every 500 generations. I don't know if it's 500 or 1,000. It's currently 34 gigabytes. And we can actually see, I checked what it was a month ago. The full snapshot was 120 gigabytes. This is compressed actually. It's grown 14 gigabytes in 1 month. The garbage collected backup was 32 gigabytes and it's now 34. So it grows much slower. It doesn't grow because we're adding blocks, we're adding transactions, and those aren't garbage related. So this is one way to mitigate the storage, and as an aside, you can actually turn on garbage collection while you're syncing as well, and that means the footprint will never really go above this. The faster way to sync would be to not garbage collect while you're syncing, because while you're syncing, basically the node is working really hard. So having garbage collection turned on during sync slows down the sync with about 30%. Yes?
Is there a certain number of nodes required to maintain unpruned copies of the table?
Is there a certain amount of nodes required to maintain an unpruned copy? By default, we don't prune. So you have to turn on garbage collection.
Suppose everybody turns on garbage collection. That's my point.
Okay, if there are, how many nodes are required? That's a good question. We don't have a limit for that. So typically miners do not do garbage collection. They run full nodes.
What is the stale state? And we don't have shape before. So there's no issue with syncing with any port. We don't need the verification also.
So we are working on some other things that will improve things in this matter. One thing is the spine sync that we're talking about, syncing only the key block headers. This is a lot faster than syncing all the state. So essentially download only the key block headers, and you validate those. The problem is at some height, you will have to switch over to a full city. So then what we do is we copy essentially, or we mimic parts of the Ethereum protocol to fetch states at a certain height. So essentially you will ask nodes to give you a subset of the state trees and then just keep fetching until you've downloaded all the live state at the height where you want to switch over to regular state. And after that, you simply go on. This is work in progress. We're kind of putting the pieces together. We had to pause and do some changes to how the nodes announce features and handle versions of the sync protocol, but that seems to be working now, so now we're piecing this together. Another thing that we're working on is, well, sometimes called jump sync. This is an alternative to the zero knowledge proof approach, where basically the idea is that when you're connecting to peer nodes and they send a ping object to you, this is how they show that they're alive. They also show the ping object contains the top hash and top difficulty so that you can know which peer seems to have the longer chain. Those are the ones you sync against. What we were thinking was that they can also announce either a proof of inclusion hash, that's a small cryptographic proof that a certain element is part of the partition Merkle tree given a certain root hash, a certain slice of the tree. So the idea there is that we maintain a block hash tree, we store all the block hashes on the chain in a Merkle tree, and then we provide at a certain height, say even 1,000 generations close to the top, a proof of inclusion and the hash is basically saying this hash at this height is in the same tree as the Genesis block. So we know it's connected to Genesis. That gives you a little bit more security, especially if several peers announce the same root hash and the same proof. Then you have kind of a majority view that this is a safe block to see. We had a discussion, the entire rate we objected that how much does that give you except just saying these are the hashes. And all the peers say this is my hash at this height. You can probably safely just fetch that height. And then you just need to make sure that the chain block insertion logic is okay with inserting a block that doesn't have a parent block. So this is a slightly bigger surgery on the core logic of the chain, because you have to basically say, well, trust us, we're doing this now, this is a jump sync, there is no parent. But that's fine. I mean, we're working on this, we're going to be testing and debugging pretty soon on this, and this should be, if it works, it should be making it possible to do a light client that very quickly jumps up to close to the top, syncs the state at that height, and then you go from there. So, I mean, currently, what are we talking about? 14 hours to sync the full chain? I don't know exactly how much faster this would be, but it would be radically fast. So, the thing about specialized chains, I think there are some things that we can discuss in basically evolving sort of community support for related but specialized chains, where each chain maybe has its own parameters in terms of performance, also perhaps storage parameters, so that you have a block or a chain that is really designed to store images or big data, reasonably big, at least for blockchain. If you have a single chain, you don't want people to store megabytes of data in each transaction, because that's going to blow up storage for everyone. But if you have partitioned Hyperchain child chains, then you can actually start partitioning and deal with it in that way. But then we may need actually sort of community functions where these chains can actually interoperate as if they were almost a single chain. There would probably be need for good autonomous swaps. Last year, I presented state channel markets with Hyperchain child chains. They could all run compatible state channels. You could actually do real-time atomic swaps, DOS, and value transfer across chains. So that will make it more attractive to do this kind of partitioning where all the code is compatible, the contract, the language is the same. And so this is something that we hope to be working on as well. So that was pretty much it. Any questions?